We might never go beyond the moon again. That celestial body we first visited over 50 years ago might represent the absolute boundary of human exploration for centuries to come, possibly forever. And the reasons why will challenge everything you thought you knew about our future among the stars. If you're fascinated by the universe and appreciate honest conversations about humanity's place in the cosmos, then subscribe to this channel and give this video a like. We're building a community of curious minds who aren't afraid to confront difficult truths about our universe. Now let's get started. When Neil Armstrong stepped onto the lunar surface on July 20th, 1969, humanity collectively believed we'd crossed a threshold. The moon was just the beginning. Mars would follow within a decade or two, Jupiter's moons by the 21st century, other star systems by the 22nd. We'd become a spacefaring civilization, spreading across the galaxy like explorers once spread across Earth's oceans. That vision hasn't materialized, not even close. The last time humans set foot on the moon was December 1972, over 50 years ago. Since then, we've stayed in low Earth orbit, circling our planet like swimmers afraid to leave the shallow end. The International Space Station orbits just 250 miles above Earth's surface. That's roughly the distance from New York to Washington, D.C. You could drive it in 4 hours. This is what we call space exploration in the 21st century. Why? Why have we retreated from the cosmos when we seemed so close to conquering it? The common explanations focus on politics, funding, and public interest. NASA's budget peaked during the Apollo era at over 4% of the federal budget. Today, it receives less than half of 1%. Political priorities shifted. The Cold War space race ended. Without competition driving urgency, moon missions seemed expensive and unnecessary. These explanations are true, but incomplete. They address the question of why we stopped going to the moon, not why we can't go much farther. Because here's the unsettling reality nobody wants to acknowledge. Even if we dedicated unlimited resources to human space exploration, even if every nation on Earth cooperated toward this single goal, even if we solved every engineering challenge we currently face, we'd still be effectively trapped within our solar system. And the moon might genuinely represent the practical limit of human presence beyond Earth. The problem is physics. Cold, unforgiving, absolute physics. Let's start with something basic that most people dramatically underestimate: distance. Not the distance to the moon, which is trivial by cosmic standards. I'm talking about the distances between stars, between solar systems, between us, and literally anywhere interesting in the universe. The moon sits about 239,000 miles from Earth. That's far by everyday standards. You could drive around Earth's equator almost 10 times to cover that distance. But in cosmic terms, it's nothing. A gentle stroll to the neighbor's house. Light from the moon reaches your eyes in about 1.25 seconds. Radio signals travel at light speed, so when astronauts on the moon spoke to Mission Control in Houston, there was roughly a 3-second round-trip delay. Noticeable, but manageable. Now consider Mars, the next target for human exploration. Mars orbits the Sun at a different distance than Earth, so the gap between our planets constantly changes. At its closest approach, Mars comes within about 34 million miles of Earth. At its farthest, it's over 250 million miles away. When we send missions to Mars, we wait for favorable orbital alignments that occur roughly every 26 months. Even then, the journey takes 6 to 9 months using current propulsion technology. That's already a massive leap in difficulty compared to the moon. The Apollo missions took 3 days to reach the lunar surface. A Mars mission requires months in deep space, exposing astronauts to dangers we'll discuss shortly. But let's continue scaling up, because Mars is still in our neighborhood. It's still part of our solar system, still bound to the same star, still reachable within a human lifetime. The edge of our solar system, if we define that as the heliopause, where the sun's influence yields to interstellar space, lies about 11 billion miles away. The Voyager 1 spacecraft, launched in 1977, crossed this boundary in 2012 after traveling for 35 years. It's now the most distant human-made object in existence, over 14 billion miles from home, and it's still sending back data. This remarkable achievement represents humanity's farthest physical reach into the cosmos. 14 billion miles sounds impressive until you realize that Voyager 1 has barely left our cosmic doorstep. The nearest star system, Alpha Centauri, lies about 25 trillion miles away. That's 25 followed by 12 zeros. It's a distance so vast that astronomers don't even measure it in miles. They use light years, the distance light travels in 1 year, moving at 186,000 miles per second. Alpha Centauri is 4.37 light-years away. Light, the fastest thing in the universe, takes over 4 years to cross that gap. Voyager 1, humanity's fastest and farthest spacecraft, is moving at about 38,000 miles per hour relative to the Sun. At that speed, it would take over 70,000 years to reach Alpha Centauri. 70,000 years. Human civilization as we know it, agriculture, cities, writing, everything we call history, has only existed for about 10,000 years. This is the first crushing reality of interstellar travel. The distances are incomprehensibly vast. Not just big, not just challenging, incomprehensibly, almost absurdly vast. The universe operates on scales that mock human ambition, but distance alone isn't the only problem. If we could somehow travel faster, if we could approach even a fraction of light speed, we could reduce these journey times dramatically. Travel at 10% of light speed, and Alpha Centauri becomes reachable in about 43 years. Still a lifetime, but conceivable. Travel at 50% of light speed, and you're there in less than 9 years. At 90% of light speed, the journey drops to just under 5 years. So why don't we build faster spacecraft? Why don't we accelerate to these incredible velocities and actually explore beyond our solar system? This brings us to the second crushing reality: energy. Physics imposes brutal requirements on anything you want to accelerate. The faster you want to go, the more energy you need. This relationship isn't linear. It's exponential. Doubling your speed requires roughly 4 times the energy. Tripling your speed requires 9 times the energy. And as you approach light speed, the energy requirements become infinite. This isn't an engineering challenge. This is fundamental physics, specifically Einstein's special theory of relativity. As objects approach light speed, their effective mass increases. The faster they go, the more energy is required to accelerate them further. At light speed itself, any object with mass would require infinite energy to accelerate. It's impossible. The universe doesn't allow it. So light speed is completely off the table for anything with mass. Fine. Let's be more modest. Let's aim for 10% of light speed, fast enough to make interstellar travel theoretically possible within a human lifetime, or at least within a few generations. Surely that's achievable with advanced enough technology, right? Let's do the math. Consider a relatively small spacecraft, something modest by space exploration standards, with a mass of about 10,000 kilograms. That's roughly the mass of the Voyager probes. To accelerate this spacecraft to 10% of light speed, about 18,600 miles per second, you'd need approximately 4.5 times 10 to the power of 18 joules of energy. What does that number mean in practical terms? It's roughly equivalent to the total energy consumption of the entire United States for an entire year, for one small probe, to reach 10% of light speed. Now consider that you'd probably want to send something larger than Voyager. You'd want redundant systems, scientific equipment, communication arrays. If you're sending humans, you need life support, radiation shielding, living quarters, food, water recycling systems, medical facilities. The mass multiplies quickly. A crude interstellar vessel might weigh hundreds of thousands or even millions of kilograms. The energy requirements scale proportionally. And remember, this is just to accelerate. If you want to actually stop at your destination, rather than flying through at relativistic speeds, you need to decelerate. That requires the same amount of energy again. So double everything I just mentioned. Where does this energy come from? Chemical rockets. The technology that took us to the moon are laughably inadequate. The space shuttle's external tank held over 500,000 gallons of liquid hydrogen and liquid oxygen. This enormous quantity of fuel lifted roughly 78,000 kilograms into low Earth orbit, a velocity of about 17,500 miles per hour. To reach interstellar velocities, you'd need fuel reserves millions of times larger than your spacecraft, which creates an impossible recursive problem. The more fuel you carry, the heavier your spacecraft becomes, requiring even more fuel. Nuclear propulsion offers better efficiency. Nuclear fission or fusion reactions release far more energy per unit of fuel than chemical reactions. Theoretical designs like nuclear pulse propulsion, where you literally detonate nuclear bombs behind your spacecraft and ride the shockwave, could potentially reach a few percent of light speed. Project Orion, seriously studied in the 1950s and 60s, explored this concept. The calculations suggested that with thousands of nuclear explosions, a massive spacecraft could eventually reach velocities around 3 to 5% of light speed. But even this radical approach faces severe limitations. The engineering challenges are immense. You'd need to build a spacecraft capable of withstanding repeated nuclear blasts. You'd need to carry thousands of nuclear devices. You'd need to solve the political and environmental problems of launching such a craft from Earth or assembling it in space. And even if you solved all these problems, 3 to 5% of light speed means a journey to Alpha Centauri would still take nearly a century. More exotic propulsion concepts exist in theoretical physics. Matter-antimatter annihilation produces energy with near-perfect efficiency, converting mass directly into energy according to Einstein's famous equation, E equals mc squared. A matter-antimatter engine could theoretically achieve much higher velocities. The problem? We can currently produce only microscopic quantities of antimatter at enormous cost using particle accelerators. Creating and storing the amounts needed for interstellar propulsion is beyond any foreseeable technology. We're talking about challenges that make building pyramids look like stacking children's blocks. Laser propulsion represents another theoretical possibility. Imagine a gigantic laser array, perhaps solar-powered, positioned in our solar system. This array focuses an intense beam onto a lightweight sail attached to a small probe. The photon pressure from the laser accelerates the sail to relativistic speeds. Breakthrough Starshot, a project announced in 2016, proposes exactly this approach. The plan involves using ground-based lasers to accelerate gram-scale probes to about 20% of light speed, potentially reaching Alpha Centauri in about 20 years. This is genuinely exciting and represents our most realistic near-term possibility for interstellar exploration. But notice what we've had to sacrifice to make it even theoretically feasible. The probes would be tiny, weighing just grams, about the mass of a butterfly. They'd carry minimal instrumentation. They couldn't slow down at their destination, just flash past at relativistic speeds, gathering data for mere hours or minutes, and they certainly couldn't carry humans. For human interstellar travel, laser propulsion faces insurmountable problems. Humans require life support, which requires mass. Radiation shielding requires mass. Everything humans need for survival requires mass. And the more mass you have, the more laser power you need to accelerate it. The energy requirements quickly become absurd. You'd need to build laser arrays covering significant portions of Earth's surface or deploy massive solar collectors in space, all focusing power on a single departing spacecraft. The infrastructure cost would dwarf every engineering project in human history combined. Even if we somehow solved the energy and propulsion problems, we'd face another brutal challenge: radiation. Space is not empty. Between the stars lies the interstellar medium, a thin soup of hydrogen atoms, cosmic dust, and high-energy particles. On Earth, we're protected from cosmic radiation by our planet's magnetic field and thick atmosphere. In deep space, there's no such protection. Astronauts on the International Space Station receive about 50 to 2,000 millisieverts of radiation per year, compared to about 3 millisieverts for an average person on Earth's surface. That's already a significant increase, carefully monitored to ensure astronauts don't exceed safe exposure limits over their careers. Now, consider travel through interstellar space at relativistic velocities. Every hydrogen atom you encounter becomes a high-energy particle from your spacecraft's perspective. At 10% of light speed, these impacts deliver considerable energy. At 50% of light speed or higher, even individual atoms become dangerous projectiles. The interstellar medium, normally harmless, transforms into a radiation storm capable of damaging both equipment and human tissue. Galactic cosmic rays pose an even greater threat. These high-energy particles, originating from supernovae and other violent cosmic events, permeate the galaxy. They're difficult to shield against because they're so energetic. On Earth, our atmosphere and magnetic field protect us. On the Moon, astronauts received higher doses but only for a few days. On a journey lasting years or decades, cosmic ray exposure becomes a serious problem. Radiation damages living cells in multiple ways. It can break DNA strands, potentially causing cancer. It can damage the central nervous system, affecting cognitive function. It increases cataract risk. High doses cause acute radiation sickness. The longer you spend in deep space, the greater your cumulative exposure and the higher your risk of severe health problems. Shielding helps, but it's not a perfect solution. Traditional radiation shielding uses dense materials like lead to absorb radiation, but adding shielding means adding mass, which requires more energy to accelerate, which requires more fuel or more powerful propulsion, which increases mission cost and complexity. There's always a trade-off, and some types of radiation, particularly high-energy cosmic rays, penetrate even substantial shielding. Advanced shielding concepts exist. Water makes excellent radiation shielding and serves the dual purpose of being essential for life support. Spacecraft designs have proposed surrounding living quarters with water tanks, providing both drinking water and protection. Hydrogen-rich materials like polyethylene also shield effectively against certain types of radiation. Active magnetic shielding, creating an artificial magnetosphere around the spacecraft, similar to Earth's protective field, has been proposed, but requires enormous amounts of power to generate and maintain over the volume needed to protect a crewed vessel. Even with the best shielding we can imagine, a multi-year or multi-decade journey exposes crew members to radiation levels far exceeding what we currently consider safe. Career astronauts receive carefully limited exposure over their entire working lives. An interstellar journey would deliver that much radiation in the first few years, with decades more exposure still to come. The health consequences would be severe and unavoidable. You might wonder about using medication or genetic engineering to increase human radiation resistance. Perhaps future biotechnology could make humans more resilient to radiation damage. This enters the realm of speculation, but even if we could modify human biology to tolerate higher radiation levels, we'd still face limits. Radiation damage is fundamentally about energy-disrupting molecular bonds. Beyond certain thresholds, no amount of biological adaptation can prevent cells from being destroyed. We might push the boundaries, but we can't eliminate the problem. Then there's the psychological challenge of confinement. The International Space Station, humanity's longest-duration space habitat, houses about 6 people in a volume comparable to a 6-bedroom house. Astronauts typically spend about 6 months aboard, though some have stayed over a year. Even with carefully selected, highly trained individuals, psychological stresses emerge. Isolation, monotony, confinement, lack of privacy, inability to go outside, distance from family, and the constant awareness that you're in a hostile environment all take a toll. Now imagine not 6 months, but 6 years, or 60 years, or 600 years. Imagine you're aboard a spacecraft the size of a large building, with perhaps dozens or hundreds of other people, with no possibility of leaving, no fresh air, no natural environment, no ability to return home. Everyone you left behind on Earth will be dead long before you arrive anywhere. If something goes wrong, you can't call for help. You're completely alone in the void between stars. Human psychology evolved for life in small social groups on Earth's surface. We need nature, sunlight, weather, seasons, the presence of other life. We need purpose and variety. Confining people in a tin can for decades or centuries, even with virtual reality or elaborate recreational facilities, pushes the boundaries of what human minds can endure. Studies of isolated environments like Antarctic research stations, submarines, and long-duration space missions consistently show psychological challenges emerging over extended periods. You could try to mitigate this through crew selection, psychological support, mission design, and creating as pleasant an environment as possible. Generation ships, vessels designed to travel for centuries with multiple generations born, living, and dying aboard, have been proposed for interstellar journeys. The original crew would never see the destination. Their grandchildren or great-great-grandchildren would be the ones to arrive. This introduces additional complications. How do you maintain mission cohesion across generations? What if later generations decide they don't want to continue the mission? What rights do children born aboard have? They never chose to be part of this journey. These aren't just engineering problems. They're profound ethical and social questions with no clear answers. Another often overlooked problem is communication. Radio signals travel at light speed, the absolute cosmic speed limit. When Apollo astronauts were on the moon, there was a roughly 3-second round-trip communication delay. Manageable, though it made conversations slightly awkward. For Mars missions, the delay ranges from about 8 minutes to over 40 minutes depending on orbital positions. Still manageable with adjustment. You send a message, wait, receive a response, wait, send another message. Conversations become more like exchanging emails than talking on the phone. Now consider an interstellar journey. At Alpha Centauri, 4.37 light-years away, radio signals take 4.37 years to reach Earth. A message saying, "We've arrived," wouldn't be heard for over 4 years. If something went wrong and the crew radioed for help, that cry for help would travel through space for over 4 years before reaching anyone, and any response or advice would take another 4 years to return. By the time help arrived, nearly 9 years would have passed. The crew would be completely on their own, unable to receive real-time guidance, unable to benefit from knowledge or technology developed after their departure. This communication lag means an interstellar mission must be essentially self-sufficient and autonomous from the moment it launches. Every possible problem must be anticipated. Every repair must be achievable with onboard resources. Every decision must be made by the crew without consulting Earth. There's no mission control to ask for help, no ability to abort and return home if things go wrong. Once you leave, you're committed absolutely. The spacecraft itself must function reliably for the entire journey duration. Consider the engineering challenge of building something that operates continuously for decades or centuries without maintenance from outside, without replacement parts beyond what you brought with you, without technical support from Earth. The International Space Station requires regular resupply missions bringing spare parts, new equipment, and materials. It's undergone constant upgrades and repairs since its initial assembly. An interstellar vessel couldn't rely on any of that. Everything it needs must be carried from the start, or manufactured aboard using raw materials also carried from the start. Redundancy helps. You design multiple backup systems so if one fails, others can take over. You bring spare parts for critical components. You include manufacturing capabilities so the crew can fabricate certain replacements. But there are limits. You can't bring backups for everything. Some components are too large, too complex, or too specialized to duplicate. And the more backups and spares you carry, the more mass you add, requiring more energy to accelerate. Bringing us back to the fundamental energy problem. Entropy works against you. Over time, systems degrade, seals leak, materials become brittle, electronics fail, chemical reactions gradually change stored substances, radiation damages components. Even with the best engineering, maintaining complex systems over decades or centuries without external support is extraordinarily difficult. Things break down. That's not a failure of design. It's thermodynamics. Order naturally decays into disorder. Fighting this requires energy and effort and materials, all of which are limited aboard a spacecraft. Consider something as basic as food and water. Humans need roughly 2 liters of water per day and about 2,000 calories of food. For a crew of 100 people on a 50-year journey, you'd need about 3.6 million liters of water and roughly 3.6 billion calories worth of food. Water can be recycled through careful engineering, collecting, purifying, and reusing every drop. The ISS already does this, achieving impressive recycling rates. But recycling is never 100% efficient. You lose small amounts to various processes, requiring reserves to compensate. Food is trickier. You could bring enough for the entire journey. But storing food for decades presents problems. Most food degrades over time. Freeze-drying and other preservation methods help, but nothing lasts indefinitely. You could bring seeds and grow food aboard, but that requires space, light, water, nutrients, and energy. Essentially, you need to build a farm in space, maintain it continuously, and ensure it produces enough to feed everyone reliably for the entire journey. Crop failures would be catastrophic. Closed-loop life support systems attempt to solve these problems by recycling everything. Water gets purified and reused. Air gets scrubbed of carbon dioxide and replenished with oxygen, possibly through plants or algae that perform photosynthesis. Waste gets processed to recover nutrients for growing food. In theory, you create a self-sustaining miniature ecosystem that can support human life indefinitely. In practice, this is incredibly difficult. Earth's biosphere is a staggeringly complex system involving billions of species interacting in ways we still don't fully understand. It's taken 4 billion years of evolution to develop these intricate relationships. We can't simply replicate that in a spacecraft. Biosphere 2, an experiment conducted in Arizona during the early 1990s, attempted to create a sealed ecological system supporting 8 people. Despite enormous resources and careful planning, the project encountered serious problems. Oxygen levels dropped unexpectedly. Carbon dioxide accumulated. Species extinctions occurred. Insects proliferated while pollinators declined. After less than 2 years, the experiment required external intervention to remain viable. If we can't maintain a closed ecosystem for 8 people for 2 years on Earth's surface, where we have access to unlimited resources and expert support, how could we possibly maintain one for hundreds of people for decades or centuries aboard a spacecraft? The challenges multiply enormously. Every variable must be controlled. Every potential failure point must be anticipated. There's no margin for error and no possibility of rescue. Some propose using hibernation or suspended animation to reduce life support requirements. If crew members spend most of the journey in a dormant state, you need far less food, water, and air. Metabolic activity drops dramatically during hibernation, reducing resource consumption to a fraction of normal levels. This would also address psychological challenges. The crew simply sleeps through the decades-long journey, awakening only near the destination. This concept appears regularly in science fiction, but the medical reality is far more complex. Some animals hibernate naturally, but humans don't. Inducing a hibernation-like state would require drugs or technologies that don't currently exist. We can put people in medically induced comas for days or occasionally weeks, but these states require careful monitoring and carry serious health risks. Extending this to months or years presents enormous medical challenges. Muscle atrophy, bone density loss, immune system suppression, and countless other physiological problems would need to be solved. And who monitors the sleeping crew? Do some stay awake in shifts? That reintroduces all the life support and psychological problems we were trying to avoid. Cryogenic freezing, literally freezing humans and reviving them later, is even more speculative. Freezing causes ice crystals to form inside cells, rupturing cell membranes and causing massive tissue damage. Some organisms can survive freezing through natural antifreeze compounds, but human tissues generally can't. We can freeze and store certain cells, tissues, and embryos using careful techniques, but freezing and successfully reviving an entire human body remains purely theoretical. No mammal has ever been frozen solid and successfully revived. This isn't a technology that's just around the corner. It's something that might be fundamentally impossible given how biological systems work. Let's assume, optimistically, that all these problems can eventually be solved through sufficiently advanced technology. Assume we develop propulsion capable of reaching 10 or 20% of light speed. Assume we create radiation shielding that adequately protects crews. Assume we solve life support for multi-decade or multi-century journeys. Assume we build spacecraft reliable enough to function across these timescales. Assume we address the psychological challenges of confinement. Even granting all these generous assumptions, we face one more fundamental barrier. Where would we go? The nearest star system, Alpha Centauri, contains 3 stars, Alpha Centauri A and B, which orbit each other closely, and Proxima Centauri, a small red dwarf orbiting the pair at a greater distance. In 2016, astronomers discovered Proxima Centauri b, a planet orbiting in the habitable zone of Proxima Centauri. This planet, roughly Earth mass, orbits at a distance where liquid water could theoretically exist on its surface. It's the closest potentially habitable world we know of. But potentially habitable doesn't mean habitable. Proxima Centauri is a red dwarf, a type of star very different from our Sun. Red dwarfs are cooler and dimmer, so their habitable zones lie much closer to the star. Proxima Centauri b orbits its star every 11.2 days, far closer than Mercury orbits our Sun. At that distance, it's likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness. One hemisphere might be scorching hot while the other is frozen. The narrow band between might have tolerable temperatures, but maintaining liquid water in such an environment is questionable. Red dwarfs are also prone to violent flares, sudden eruptions of radiation, and charged particles far more intense than anything our Sun produces. These flares regularly bombard planets in close orbits, stripping away atmospheres and bathing surfaces in deadly radiation. Proxima Centauri b, despite being in the habitable zone, might be utterly inhospitable due to this stellar violence. We simply don't know yet. We can't observe the planet's surface or atmosphere in enough detail to determine actual conditions. Even if Proxima Centauri b turns out to be genuinely habitable, even if it has breathable atmosphere, tolerable temperatures, liquid water, and protection from radiation, it's still 4.24 light-years away. At 10% of light speed, the journey takes 42 years. At 20% of light speed, still 21 years. An entire human generation or more, spent traveling to a destination that might turn out to be uninhabitable after all. And we've only been talking about the closest star system. The vast majority of stars lie far more distant. The next nearest stars after Alpha Centauri include Barnard's star at 6 light-years, Wolf 359 at 7.9 light-years, and Leyland 21,185 at 8.3 light-years. Within 20 light-years of Earth, there are only about 133 star systems. Most are dim red dwarfs. Only a handful are similar to our Sun. The odds of finding another Earth, a planet with the right size, the right temperature, the right atmosphere, liquid water, and a stable environment conducive to life, are not favorable even with hundreds of candidates. Mars, by comparison, is a known quantity. We've sent numerous probes and rovers. We've mapped its surface extensively. We understand its geology, climate, and resources. We know Mars is hostile, cold, dry, bathed in radiation, with an atmosphere too thin to breathe. But we also know it has water ice, useful minerals, and enough resources that a self-sustaining colony is at least theoretically possible with sufficient technology and effort. Mars is difficult but achievable. It represents the frontier of realistic human expansion. Beyond Mars lie the asteroid belt and the outer solar system. Jupiter's moon. Europa harbors a subsurface ocean beneath its ice shell. Saturn's moon, Enceladus, similarly contains liquid water. These moons might support microbial life and could potentially be resources for future expansion. Even without native life, they offer water and other materials. The asteroid belt contains vast mineral wealth, iron, nickel, platinum, and other valuable resources in quantities that dwarf Earth's accessible reserves. Our solar system, in other words, contains enough resources and enough interesting destinations to occupy human exploration and expansion for centuries or millennia. We could build habitats on Mars, establish mining operations in the asteroid belt, construct floating cities in Venus's upper atmosphere where temperatures and pressures are surprisingly Earth-like, explore the ocean worlds of the outer solar system, and create vast rotating space stations at various locations. A solar system-spanning civilization would be a tremendous achievement, representing an enormous expansion of humanity's presence beyond our home planet. This might be our actual future. Not a galaxy-spanning empire visiting countless worlds, but a carefully developed solar system civilization making full use of our cosmic neighborhood. Not Star Trek, but something perhaps more realistic and ultimately more sustainable. And maybe that's enough. Maybe that's what the universe allows for technological civilizations, thorough development and utilization of their home star systems, with interstellar space remaining a barrier that only information, not living beings, can readily cross. We can still explore beyond our solar system through remote observation and robotic probes. Our telescopes grow ever more powerful. The James Webb Space Telescope, launched in December 2021, observes the universe in infrared wavelengths with unprecedented clarity. It can analyze the atmospheres of exoplanets, planets orbiting other stars, looking for chemical signatures that might indicate life. Future telescope projects will push these capabilities further, potentially allowing us to image exoplanet surfaces, to watch weather patterns on distant worlds, to search for industrial pollution or artificial lights that might betray technological civilizations. Robotic probes can venture where humans cannot. Voyager 1 and 2, launched in 1977, continue operating nearly 50 years later, sending data from interstellar space. Future probes, perhaps using laser propulsion like Breakthrough Starshot proposes, might reach nearby stars within decades. These missions wouldn't return data immediately. A probe reaching Alpha Centauri in 20 years would still need 4.37 additional years for its signals to reach Earth, but within a human lifetime, we could receive close-up images and data from another star system. We could know whether planets there truly harbor life or suitable conditions for it. This represents a form of exploration, slower, more patient, mediated through machines rather than direct human presence, but genuinely expanding our knowledge of the cosmos. We could map nearby star systems, catalog their planets, search for biosignatures, and build an understanding of our galactic neighborhood, even if we never physically visit it. Information travels at light speed, the cosmic speed limit. While we can't easily send humans across interstellar distances, we can send data, and data carries knowledge. Perhaps this is how civilizations truly explore the galaxy. Not through physical expansion, which physics makes brutally difficult, but through observation and communication. A sufficiently advanced civilization could build enormous telescopes, perhaps planet-sized instruments using gravitational lensing or interferometry techniques we're only beginning to explore. Such instruments might observe distant worlds with incredible detail, watching their surfaces, studying their atmospheres, searching for signs of life or intelligence. If other technological civilizations exist in the galaxy, they face the same physical barriers we do. The laws of physics don't change based on who you are or how advanced your technology becomes. Einstein's equations apply universally. The speed of light is the speed of light for everyone. Energy requirements for acceleration don't diminish just because you're clever. This suggests that other civilizations, if they exist, are probably similarly confined to their home star systems, observing the galaxy but not traveling across it. This provides one possible answer to the Fermi paradox, the famous question asked by physicist Enrico Fermi: where is everybody? If life is common in the universe, and if intelligence occasionally evolves, and if technological civilizations sometimes emerge, then the galaxy should be teeming with them. Some would be millions or billions of years older than us, giving them enormous time to spread across the galaxy. Yet we see no evidence of their presence. No megastructures, no clearly artificial signals, no visitors. The galaxy appears empty and silent. Many explanations have been proposed for this apparent absence. Perhaps life is extremely rare. Perhaps intelligence rarely evolves. Perhaps technological civilizations typically destroy themselves before spreading beyond their home worlds. These are sobering possibilities, each carrying implications about our own future. But another explanation is simply that interstellar travel is so difficult that civilizations don't spread much beyond their home systems. They develop their local resources, observe the galaxy, perhaps communicate across interstellar distances, but don't physically colonize other stars because the energy costs and timescales make it impractical. This doesn't mean they're not out there. It means they're home, just as we are. Separated by distances so vast that physical meeting becomes effectively impossible, even for civilizations millions of years more advanced than us. The galaxy could be full of life, full of intelligence, full of technological civilizations, all confined to their respective star systems, all gazing at the cosmos and wondering if anyone else exists, all unable to bridge the immense gulfs between stars. Radio communication offers a way to potentially connect across these distances. Radio waves travel at light speed, so a signal sent to Alpha Centauri arrives in 4.37 years. Slow by human standards, but infinitely faster than sending a spacecraft. Since the 1960s, SETI, the search for extraterrestrial intelligence, has scanned the skies for radio signals that might indicate technological civilizations. So far, we've heard nothing definitive, but we've searched only a tiny fraction of the sky at a limited range of frequencies. The galaxy is enormous, and radio searches require patience and persistence. If we detected a signal from another civilization, even one hundreds or thousands of light years away, it would transform our understanding of our place in the universe. We'd know we're not alone. We couldn't meet them, couldn't visit their worlds, couldn't shake their appendages or share a meal. But we could communicate, exchanging information across the light years. They could tell us about their world, their biology, their history, their science, their culture. We could tell them about Earth, about humanity, about our own journey from the savannah to the stars. The conversation would be incredibly slow, each exchange taking years, decades, or centuries depending on the distance, but it would be a conversation nonetheless. Some scientists and philosophers argue we should actively broadcast messages to potential civilizations rather than just listening. METI, messaging to extraterrestrial intelligence, involves deliberately sending powerful radio transmissions toward nearby stars or the galactic center, announcing our presence and inviting response. Others worry this is dangerous, that advertising our existence to unknown entities could invite unwanted attention from hostile civilizations. This debate continues, balancing the potential benefits of contact against the uncertain risks. Personally, given what we know about the difficulties of interstellar travel, the risk seems minimal. Even if a hostile civilization received our transmissions and wanted to respond with violence, the practical barriers to reaching us are the same ones we face. They can't simply hop in a spaceship and arrive here next year. The journey would take centuries at minimum, require enormous resources, and face all the same challenges we've discussed. By the time they arrived, if they could arrive at all, humanity would be so different, either extinct or transformed, that the original message would be ancient history. More likely, any civilization capable of interstellar travel would also be wise enough to understand that resources exist abundantly throughout the galaxy. There's no logical reason to travel light years to conquer one specific world when countless uninhabited star systems offer the same resources without the complications of dealing with native inhabitants. The universe is not a zero-sum game. It's incomprehensibly vast, filled with more stars, more planets, and more resources than any civilization could ever exhaust. Conflict over territory makes sense when space is limited. In a galaxy of 400 billion stars, space is anything but limited. This brings us back to Earth, to our solar system, to the Moon. If interstellar travel is effectively impossible, if we're realistically confined to our cosmic neighborhood, then our immediate surroundings become infinitely more precious. The Moon isn't just the first step toward the stars. It might be one of the few destinations we'll ever actually reach with human feet. The Moon sits just 3 days away. Using Apollo-era technology, it's close enough that communication happens in real time. It's close enough that rescue missions are theoretically possible. It's close enough that we can ship supplies, rotate personnel, and maintain continuous presence with manageable resources. And yet we abandoned it over 50 years ago and haven't returned since. Current plans aim to change this. NASA's Artemis program intends to return humans to the lunar surface, establishing a sustainable presence rather than brief visits. The goal is to build a lunar base, to learn how to live and work on another world, to utilize local resources like water ice in permanently shadowed craters. The Moon can serve as a testing ground for technologies and techniques needed for Mars and beyond. It can host scientific instruments, particularly radio telescopes on the far side where Earth's radio noise is blocked. It can provide resources. The lunar regolith contains oxygen bound in minerals, and with sufficient energy, this oxygen can be extracted for life support and rocket fuel. But Artemis faces delays and budget uncertainties. The first crewed landing, originally planned for 2024, has been pushed to 2027 or later. The program's long-term funding remains uncertain, dependent on political priorities that shift with each election cycle. We've been here before, ambitious plans announced with great fanfare, only to be scaled back or cancelled when budgets tighten or administrations change. The Moon has been promised and abandoned multiple times in the decades since Apollo. Why is it so difficult to maintain commitment to space exploration? Part of the answer is psychological. The Moon landing in 1969 was a triumph, but it was also a conclusion. We'd achieved the goal set by President Kennedy in 1961, landing a man on the Moon and returning him safely to Earth before the decade ended. Once accomplished, the driving motivation evaporated. Subsequent landings generated diminishing public interest. By Apollo 17, the final mission, television networks barely covered it. The public had moved on. Maintaining public and political support for long-term projects is difficult in democratic societies where leadership changes regularly and immediate concerns compete for attention and resources. Healthcare, education, infrastructure, defense, social programs, all these demand funding. Space exploration, while inspiring, doesn't directly address pressing problems most people face daily. When budgets are tight, politically, it's easier to cut space programs than social services or defense. This isn't unique to space exploration. Many long-term projects suffer from the same problem. Climate change mitigation requires sustained effort over decades, but political systems struggle to maintain focus beyond the next election. Scientific research often operates on timescales longer than political cycles, creating funding instability. Infrastructure maintenance is perpetually underfunded because fixing bridges and roads is less politically appealing than building new things. We're not very good, as a species, at sustained commitment to projects whose benefits lie decades in the future. Space exploration suffers additionally from appearing disconnected from everyday life. Most people don't see direct benefits from missions to the Moon or Mars. The technology spin-offs, memory foam, water purification systems, improved solar panels, medical imaging advances, and countless other innovations originally developed for space that now benefit society, are real but not obviously connected to their source. People use GPS satellites constantly without thinking about space technology. They receive weather forecasts from orbital satellites without considering the infrastructure required. The benefits of space exploration are real and substantial, but they're often invisible or taken for granted. Perhaps a better approach would be emphasizing what space exploration tells us about Earth. Studying other planets teaches us about our own. Mars's climate history, including the loss of its atmosphere and liquid water, informs our understanding of atmospheric physics and climate change. Venus, despite being nearly Earth's twin in size, became a hellish greenhouse world with surface temperatures hot enough to melt lead. Understanding why helps us appreciate the delicate balance that keeps Earth habitable. The Moon's geology reveals information about the early solar system, including Earth's formation. Asteroid studies inform planetary defense, learning how to detect and potentially deflect asteroids that might threaten Earth. The perspective gained from seeing Earth from space has been profoundly influential. The famous Earthrise photograph taken by Apollo 8 astronauts in 1968, showing our blue world rising above the Moon's barren horizon, became an icon of the environmental movement. Astronauts consistently report that viewing Earth from orbit, a fragile sphere of life suspended in the void, changes their perspective on humanity's divisions and shared fate. This overview effect doesn't directly solve problems, but it provides a context that reminds us of our common home and shared future. Perhaps emphasizing this perspective would help maintain commitment to space exploration, not framing it as escape from Earth or conquest of new worlds, but as deepening our understanding of the cosmic context we inhabit. Every question we ask about the universe ultimately connects to the question of who we are and where we came from. Why do stars shine? Because nuclear fusion in their cores creates the energy that lights the cosmos, and also creates the elements necessary for planets and life. Where do we come from? From stardust, literally. The atoms in your body were forged in stars that died billions of years ago, scattering their enriched material to form new stars, planets, and eventually you. This isn't poetry or metaphor. It's physics. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stellar furnaces or supernova explosions. You are made of atoms that once existed in stars scattered across the ancient galaxy. Those atoms came together to form the Sun and planets 4.6 billion years ago. On Earth, through chemistry and biology we're still working to fully understand, those atoms organize themselves into life, into ecosystems, into consciousness, into you. You are the universe observing itself. That's not mysticism, it's straightforward fact. You're made of the universe's atoms, arranged in a configuration complex enough to ponder its own existence. When you look at the stars, you're looking at your ancestral home. When you ask questions about the cosmos, you're participating in the universe's ongoing self-discovery. This has always been true, but we've only understood it for the last century or so, since quantum mechanics and nuclear physics revealed how stars work and where elements come from. This understanding fundamentally changes how we think about our relationship to the cosmos. We're not separate from the universe, looking at it from outside. We're part of it as much as stars and galaxies are. The same physical laws that govern the motion of galaxies also govern the chemistry of your cells. The same forces that shape the evolution of stars also shape the evolution of life. Everything connects. Everything is part of one grand, interconnected cosmic story that began 13.8 billion years ago with the Big Bang and continues today. The Big Bang itself represents one of science's most remarkable discoveries. In 1929, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This implies the universe is expanding. If you run the expansion backward in time, everything converges to a point, an initial moment of extreme density and temperature from which space, time, matter, and energy all emerged. This wasn't an explosion in space, but an expansion of space itself, carrying matter and energy along with it. Evidence supporting the Big Bang comes from multiple independent sources. The cosmic microwave background, faint microwave radiation filling all space, is the cooled remnant of the intense heat from the universe's early moments. Its properties match theoretical predictions precisely. The abundance of light elements, hydrogen, helium, and traces of lithium, matches what should have formed in the first few minutes after the Big Bang. The large-scale structure of galaxies, how they cluster and distribute themselves across cosmic distances, matches computer simulations of how matter should have evolved under gravity over billions of years. We understand the universe's history from fractions of a second after the Big Bang to the present day with remarkable confidence. In the first second, the universe cooled from unimaginable temperatures, allowing quarks to combine into protons and neutrons. In the first 3 minutes, nuclear fusion briefly occurred throughout space, forming the first atomic nuclei. For the next 380,000 years, the universe was too hot for atoms to form. Electrons couldn't stay bound to nuclei. Light couldn't travel far because it constantly scattered off free electrons, making the universe opaque like a thick fog. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, light could suddenly travel freely. This moment, called recombination, released the radiation we now observe as the cosmic microwave background. From that point forward, the universe was transparent. Matter, no longer supported by radiation pressure, began collapsing under gravity into increasingly dense regions. These became the first stars and galaxies, forming several 100 million years after the Big Bang. Those first stars were massive and short-lived. They contained only hydrogen and helium, with trace amounts of lithium, the only elements produced in the Big Bang. Everything else, every element heavier than lithium, was made later in stars. Nuclear fusion in stellar cores creates heavier elements up to iron. Elements beyond iron require even more extreme conditions, supernova explosions, neutron star collisions, and other violent events where enough energy exists to forge the heaviest elements. When those first massive stars exhausted their fuel, they exploded as supernovae, scattering newly created elements into space. Later generations of stars formed from this enriched material, carrying heavier elements from their birth. Planets formed from the leftover material surrounding young stars. Rocky planets like Earth are made primarily of elements created in stars: iron, silicon, oxygen, magnesium, and countless others. Life emerged from these elements, particularly carbon, oxygen, nitrogen, hydrogen, phosphorus, and sulfur, all made in stars. This cosmic chemical enrichment took billions of years. The universe had to form stars, those stars had to live their lives and die, and their remnants had to mix with pristine hydrogen and helium to form new stars and planets enriched with heavy elements. Earth formed 4.6 billion years ago, about 9 billion years after the Big Bang. Life emerged remarkably quickly after that. The earliest evidence for life on Earth dates to at least 3.5 billion years ago, possibly earlier. Life didn't wait for ideal conditions. It emerged as soon as conditions became remotely tolerable. What does this tell us? It suggests life might be common in the universe. If life appeared quickly on Earth, as soon as water existed and the bombardment from asteroids and comets subsided enough to allow stability, then perhaps life emerges readily wherever conditions permit. Earth isn't particularly special. It's a rocky planet orbiting an average star in the outer regions of a typical galaxy. If life arose easily here, it might arise easily elsewhere too. But, and this is crucial, complexity takes time. Life on Earth remained single-celled for roughly 3 billion years. Complex multicellular life appeared only about 600 million years ago. Animals recognizable to us emerged in the Cambrian explosion around 540 million years ago. Humans appeared within the last few 100,000 years. Intelligence and technology are extremely recent, occupying a tiny sliver of Earth's history. This timeline suggests that while simple life might be common, complex life and intelligence might be rare. Every step toward complexity requires specific conditions and often involved unlikely events. The origin of complex cells, called eukaryotes, probably required one cell engulfing another in a symbiotic relationship that gave rise to mitochondria, the powerhouses of modern cells. This might have happened only once in Earth's history. All complex life on Earth shares the same mitochondrial ancestry. If such events are genuinely rare, requiring billions of years and extraordinary luck, then planets might commonly host microbial life while remaining devoid of anything more complex. Intelligence represents another filter. Many successful species on Earth show no trend toward human-like intelligence. Intelligence is metabolically expensive. Human brains consume about 20% of our energy, despite being only 2% of our body mass. Intelligence requires specific evolutionary pressures favoring it despite its costs. On Earth, social behavior, tool use, language, and complex problem-solving evolved together in ways we're still working to understand. This might be a rare combination that seldom emerges even when complex life exists. Technology represents yet another filter. Many intelligent species exist on Earth. Dolphins, elephants, crows, octopuses, and others demonstrate remarkable cognitive abilities. But only humans developed technology capable of transforming our environment and reaching beyond our planet. This required not just intelligence, but specific combinations of manual dexterity, social cooperation, communication abilities, and possibly other factors we haven't identified. Even with these advantages, human technological civilization emerged only 10,000 years ago, and spacefaring capability only in the last 60 years. This series of filters might explain the Fermi paradox. Perhaps life is common, but complex life is rare. Perhaps complex life is relatively common, but intelligence is rare. Perhaps intelligence emerges occasionally, but technological civilization rarely develops. Perhaps technological civilizations emerge sometimes, but typically destroy themselves or stagnate before spreading far. At each stage, a filter reduces the number of candidates that proceed to the next level. By the time you reach civilizations capable of interstellar communication or travel, the numbers might be very small. Alternatively, maybe we're simply early. The universe is 13.8 billion years old, but it will continue for trillions of years, perhaps forever depending on its ultimate fate. Stars will keep forming, planets will keep forming, and opportunities for life will keep arising for billions of years into the future. Perhaps most civilizations that will ever exist haven't emerged yet. We might be among the first technological species in our galaxy, looking out at a cosmos that will someday teem with life, but hasn't yet had time to develop much. This perspective is simultaneously humbling and empowering. Humbling because it emphasizes our cosmic youth and the vast scales of space and time that dwarf our brief existence. Empowering because it suggests our actions matter. We're not latecomers to a crowded galaxy, but pioneers exploring a universe still in its infancy, at least from a biological perspective. The question of whether we'll go beyond the moon connects to these deeper questions about life, intelligence, and our cosmic future. If technological civilizations are rare, then humanity represents something precious, a brief flickering of consciousness in a mostly dark cosmos. Our survival and flourishing would carry cosmic significance. Our extinction would mean the loss of something that might not arise again in this region of space for millions or billions of years, if ever. But if we're confined to our solar system by the laws of physics, does that diminish our significance? I don't think so. Our solar system contains wonders enough for any civilization. 8 planets, hundreds of moons, millions of asteroids and comets, each with unique characteristics worth studying. Mars holds clues to past habitability and possibly past life. Europa and Enceladus harbor subsurface oceans that might shelter life today. Titan has lakes and rivers of liquid methane, a bizarre chemistry utterly unlike Earth's that might support exotic forms of life. The asteroid belt contains resources sufficient for building enormous space habitats housing populations far larger than Earth's. Consider the concept of O'Neill cylinders, proposed by physicist Gerard O'Neill in the 1970s. These are enormous rotating space habitats, cylinders several miles in diameter and perhaps 20 miles long, spinning to create artificial gravity through centrifugal force. The interior surface would become the ground, with atmosphere held in by the structure's rotation. Mirrors would reflect sunlight inside, creating day-night cycles. With sufficient size, you could create Earth-like environments in space. Parks, forests, rivers, cities, entire ecosystems. The resources in the asteroid belt could theoretically construct thousands or millions of such habitats, housing a total population in the trillions. This wouldn't require any physics we don't understand. No exotic materials, no breakthrough discoveries. It's simply large-scale engineering using known principles. The limiting factors are energy, automation, and time. But given centuries or millennia to work with, utilizing solar power and increasingly sophisticated robotics, a spacefaring civilization could gradually transform the solar system into a vast network of inhabited structures. This represents a different vision of humanity's cosmic future than Star Trek-style interstellar exploration. Rather than spreading thinly across many star systems, we'd develop our home system intensively, creating habitats tailored to our needs rather than trying to terraform hostile planets. Rather than investing enormous energy reaching other stars, we'd invest that energy building infrastructure where we already live. Such a civilization would be effectively immortal in the sense that no single catastrophe could destroy it. Earthbound humanity faces existential risks: asteroid impacts, supervolcano eruptions, nuclear war, pandemic disease, climate change, artificial intelligence gone wrong. These risks are real and deserve serious attention. But a civilization distributed across the solar system in thousands of independent habitats couldn't be wiped out by any single event. Even catastrophic damage to Earth wouldn't necessarily end humanity if substantial populations existed elsewhere. This provides a compelling reason for space expansion, even without the dream of reaching other stars. Ensuring long-term survival requires not putting all our eggs in one planetary basket. Multiple independent settlements in different locations create redundancy and resilience. This doesn't require traveling light years. It just requires spreading throughout our solar system, establishing permanent, self-sufficient communities on multiple worlds and in multiple habitats. We're nowhere near this yet. Currently, humanity exists entirely on Earth except for a handful of people on the International Space Station at any given time, and they're completely dependent on Earth for survival. We haven't established any self-sufficient off-world settlements. We haven't demonstrated the ability to live permanently anywhere except Earth's surface. The gap between where we are and a solar system-spanning civilization is enormous, but it's not impossible. Nothing about this vision violates physics. Every component involves known science and engineering, scaled up and refined, but not fundamentally different from things we've already done. Building a Mars base is difficult but achievable with sufficient resources and commitment. Building asteroid mining infrastructure is challenging but feasible. Building large space habitats requires solving engineering problems, not discovering new physics. The question is whether we'll choose to pursue this path. Space exploration and development require sustained investment over generations. The benefits accrue slowly, with early phases offering little return and later phases potentially transforming civilization. This is the opposite of how modern economics and politics typically operate, which focus on short-term returns and immediate benefits. Perhaps the answer lies in changing how we think about space. Not as a place to escape Earth's problems, but as a frontier that can provide resources, knowledge, and opportunities for growth. Not as something separate from Earth, but as an extension of human civilization that remains connected to its home world. Not as a destination that replaces Earth, but as additional space that supplements and supports Earth. The Moon fits perfectly into this framework, close enough to remain connected to Earth, far enough to provide experience living on another world. Rich in resources including water ice, metals, and most importantly, space itself. Room to build, experiment, and learn, without environmental concerns like those on Earth. The Moon could host scientific instruments impossible to operate on Earth, particularly radio telescopes taking advantage of the far side's radio silence. It could serve as a construction site for larger spacecraft, taking advantage of low gravity and no atmosphere. It could become a testbed for closed-loop life support, in-situ resource utilization, and all the other technologies needed for permanent off-world settlements. Current space programs from multiple nations and private companies are targeting the moon for exactly these reasons. NASA's Artemis program aims for sustainable lunar presence. China has conducted successful robotic lunar missions and announced plans for crewed bases. India, Japan, and the European Space Agency have lunar ambitions. Private companies like SpaceX, Blue Origin, and others are developing technologies specifically for lunar missions. This renewed lunar interest differs from Apollo. Apollo was a sprint, a race to prove capability and achieve a symbolic goal. The current approach aims for permanence, for building infrastructure that enables long-term presence rather than brief visits. This requires different technologies and different strategies, but it's more aligned with genuine expansion beyond Earth. Yet progress remains frustratingly slow. Artemis faces continual delays. Budgets fluctuate with political winds. Private space companies, while promising, haven't yet delivered humans beyond low Earth orbit. We're still in the early stages, with much work remaining before lunar bases become reality. And Mars, often discussed as the next target after the Moon, represents a far greater challenge than the Moon does. Mars sits orders of magnitude farther than the Moon. The journey takes months rather than days. Communication delays make real-time control from Earth impossible, requiring more autonomous systems. The environment, while similar in some ways to the Moon, differs in crucial respects. Mars has weather, dust storms that can blanket the planet for months, affecting solar panels and equipment. Its thin atmosphere creates unique challenges, thick enough to cause problems during landing, too thin to provide meaningful protection from radiation or enable aircraft to fly easily. Mars also lies at variable distances from Earth depending on orbital positions. During favorable alignments, the journey might take 6 to 9 months. During unfavorable periods, it could take much longer or be impractical. Launch windows for efficient Mars missions occur only every 26 months. This means if something goes wrong, you can't simply send help or supplies quickly. Martian settlers would need to survive extended periods without any possibility of resupply from Earth. Despite these challenges, Mars offers advantages the Moon lacks. It has an atmosphere, albeit thin, about 1% of Earth's atmospheric pressure. This atmosphere contains carbon dioxide that could be processed into oxygen and methane for life support and rocket fuel. Mars has more gravity than the Moon, about 38% of Earth's compared to the Moon's 17%. While still low, this might make long-term health consequences less severe. Mars has 24-hour days, similar to Earth, simplifying agriculture and human circadian rhythms compared to the Moon's 29.5-day cycle. Most importantly, Mars might have hosted life in the past, and might possibly harbor microbial life today. Ancient Mars had liquid water flowing on its surface. We know this from orbital observations showing ancient river valleys, lake beds, and deltas. Rovers have found minerals that form only in the presence of liquid water. The planet was warmer, wetter, and more Earth-like billions of years ago. What happened to that water? Some escaped to space. Much more remains frozen at the poles and underground. Liquid water might still exist in subsurface aquifers. If life arose on Mars during its wet period, did it survive the transition to the current cold, dry environment? Might Martian microbes persist underground where conditions remain more favorable? This is one of the most profound questions in astrobiology. Finding life on Mars, even extinct life, would prove that abiogenesis, the natural origin of life from non-living chemistry, can occur independently on different worlds. It would suggest life might be common throughout the universe wherever conditions allow. Finding extant life on Mars would be even more significant. It would mean life can adapt to extraordinary changes, surviving planetary transformation from habitable to hostile conditions. It would provide a second example of biology to compare with Earth life, allowing us to determine what aspects of life are universal and what aspects are specific to Earth's particular path. This knowledge would revolutionize our understanding of biology and our estimates for how common life might be elsewhere. But here's the ethical complication. If Mars harbors native life, should we colonize it? Does life on Mars, even simple microbial life, have intrinsic value that should be protected from human contamination? We've already sent robots that, despite sterilization procedures, undoubtedly carried some Earth microbes. If we send humans, we'll bring entire ecosystems of bacteria, fungi, and other organisms that live on and in our bodies. We can't sterilize humans the way we sterilize spacecraft. Planetary protection protocols exist specifically to address these concerns. Current guidelines distinguish between robotic and crewed missions, between different regions of Mars, and between different mission types. Areas with high probability of liquid water receive stricter protection. Robotic missions undergo thorough sterilization, but crewed missions create complications that protocols haven't fully resolved. Humans are walking biospheres, constantly shedding microorganisms. Any substantial human presence on Mars will inevitably contaminate it with Earth life. If Mars is sterile, if no native life exists, this contamination poses no ethical problem. We'd simply be bringing life to a dead world. But if Martian life exists, even in limited locations, we risk overwhelming it with invasive Earth organisms better adapted to competition. This would be an irreversible loss, the extinction of an entire independent genesis of life, something that might be rare beyond measure. Some argue we should thoroughly search Mars robotically before sending humans, ensuring we know whether native life exists. Others point out this could take centuries and might never provide complete certainty. Life might exist in locations we haven't searched, in forms we didn't anticipate, dormant in ways we didn't detect. Meanwhile, confining humanity to Earth for centuries seems risky given the existential threats we face. Perhaps the solution involves careful zoning, designating certain regions of Mars as protected wilderness where human presence is prohibited, while developing other regions for settlement. This parallels how we manage Earth, protecting some areas as nature preserves while developing others. It's not a perfect solution. Contamination might spread beyond designated areas, but it balances the desire to expand into space with ethical obligations toward potential native life. These questions extend beyond Mars to every world we might visit. Europa's subsurface ocean likely harbors more liquid water than all of Earth's oceans combined. If life exists there, it would represent yet another independent origin, extraordinarily valuable for understanding life's cosmic prevalence. But piercing Europa's ice shell to explore that ocean risks contaminating it with Earth microbes. How do we explore responsibly while minimizing contamination risk? Enceladus poses similar questions. This small moon of Saturn sprays water geysers into space from its subsurface ocean. Spacecraft can fly through these geysers and analyze their composition without landing. We've already done this with the Cassini mission. But detailed exploration would eventually require more invasive investigation, again raising contamination concerns. These ethical dilemmas stem from our growing recognition that Earth life might not be unique, that the universe might harbor many living worlds, and that our actions carry consequences for cosmic ecology we're only beginning to appreciate. Previous generations of space exploration didn't worry much about contamination because they assumed space was sterile. We now know better. The universe might be far more alive than we thought, and that changes our ethical obligations. Returning to the original question, will we go beyond the Moon? The answer is layered and complex. Physically, we can certainly reach Mars and other solar system destinations. We have the technology in principle, if not yet in refined, reliable form. We could establish bases on Mars, explore the asteroid belt, visit the moons of Jupiter and Saturn, and spread throughout our solar system over the coming centuries. But will we? That depends on factors beyond physics and engineering. It depends on whether we maintain political will and economic commitment across generations. It depends on whether we solve the ethical questions about contaminating potentially living worlds. It depends on whether space development produces returns that justify continued investment, or whether competing priorities perpetually postpone expansion. It depends on whether we survive the various existential risks we face: climate change, nuclear war, engineered pandemics, artificial intelligence alignment problems, and others we might not have anticipated yet. A civilization that destroys itself won't colonize space. A civilization that barely survives, limping into a diminished future, might lack the resources and motivation for space expansion. But if we navigate these challenges successfully, if we mature as a species and develop the wisdom to match our technology, then yes, we can and probably will go beyond the moon. Not in the Star Trek sense of visiting countless alien worlds and meeting exotic civilizations. Physics makes that implausible. But we can thoroughly explore and develop our solar system, creating a spacefaring civilization that spans multiple worlds and countless space habitats. This isn't a lesser accomplishment. Our solar system contains more territory, more resources, and more opportunities than any civilization could exhaust in millennia. A solar system spanning humanity would represent something genuinely new in the cosmos, life that evolved on one world successfully adapting to thrive across an entire stellar system. We might never shake hands with aliens on distant worlds. We might never travel faster than light or explore the galaxy the way science fiction imagined. But we might do something equally remarkable: transform our corner of the cosmos, create a robust, multi-world civilization, and ensure that intelligence and consciousness, having emerged through billions of years of cosmic evolution, persist and flourish for billions more. The moon represents the first step on this journey. Not the only step, not the final destination, but the crucial beginning. Every journey starts with a single step, and for humanity's expansion into space, that step is returning to the moon, this time to stay. We left footprints there 50 years ago. The question is whether we'll return to make them permanent, to build on what was begun, to take the next steps toward becoming truly spacefaring. The physics allows it. The technology is achievable. The resources exist. The question is whether we choose to pursue this path, whether we commit to the long-term vision of humanity expanding beyond its birth world. I believe we will, not because it's easy, but because it's human nature to explore, to push boundaries, to seek new frontiers. We've done it throughout history, crossing oceans, traversing continents, climbing mountains, diving into ocean depths. Space is simply the next frontier, more challenging than any before, but equally compelling. The moon awaits. Mars beckons. The asteroid belt holds riches beyond imagination. The outer solar system conceals mysteries we've barely begun to uncover. And beyond our solar system, though we may never visit in person, lies a universe of 400 billion galaxies, each containing hundreds of billions of stars, many hosting planets where other forms of life might have emerged, might be evolving, might be asking the same questions we are. We stand at a unique moment in human history and cosmic history. For the first time, a species on Earth has developed the capability to leave its home world and establish a presence elsewhere. Whether we use that capability determines not just our future, but potentially the future of consciousness and intelligence in this entire region of the galaxy. The choice is ours. The moon is waiting. What happens next depends on what we decide to do, starting now. Speaking of life elsewhere in the cosmos, what if we've already found it? I invite you to watch the video on the screen, where I explore one of the most intriguing exoplanet discoveries and what it might mean for the future of humanity and the search for extraterrestrial life. The implications are profound, and they connect directly to everything we've discussed about our cosmic future.